This is Bill Foote. It is Stats 1, and we are up to Lecture 6. Welcome. This is the point where in this series, we begin to collect, aggregate, revise, and extend what we have been doing up to this point. In a sense, we've been doing that all along, but we're not going to derive yet another distribution. We have enough distributions for the moment. At least to handle single series, univariate. Multivariate, we've got to add a few more pieces to that story in order to make that one make any kind of sense. And I'm calling this Great Expectations because we're going to use what we learned in Lecture 5 to compute, to estimate a point, one point in a series, and say that is the expectation. That is our expectation. Now we can expand that idea into expectations of a range very, very easily. But right now, we just want to get to a very, very simple concept of an expectation. And it will be as simple as calculating a weighted average. The weighted average by itself is not an expectation. The expectation is when we put some life into what it is we are calculating. We're going to call the weights plausibilities. We're going to call weighted average of the thing, the average itself. What we're averaging, we're going to call outcomes. We've already come up with this. We've already done most of the hard work for this. But I have to say one more thing. This is not an academic exercise. Just about everything I'm talking about in any of these lectures comes from work done in the field. I feel often like I'm a bit of an anthropologist. I'm an economist by training, very practical economist. I used to be very impractical at one time. But if I wanted to study the Federal Reserve System, I would actually go to the Federal Reserve, talk to the people in that central bank about what they do. And out of that would come some interesting questions, the posing of the question. It's always in a context. And to the extent that I understood what they were doing, in my case, my first truly independent piece of research was around the impact of money supply announcements on stock prices, the Dow Jones. I had to understand the workings of the Fed in order to do that. I had to get my hands dirty. I actually had to talk with people. I had already come from banking, so I had a pretty good idea of the language of that particular game called banking. So I could talk, I could listen, I could formulate, I could pose. And of course, then I worked with other bankers. A lot of those other bankers have come in the methods I used, which derived from them and extended their methods. A lot of them are Federal Reserve governors. They're actually in the business of being central bankers. This illustrates a point that Jane Goodall made a long time ago about studying chimpanzees in Gobi Valley. Tukey had asked her to do this, and you could. The old way of doing this was you capture a bunch of chimpanzees, put them in a cage, and observe their behavior. Look at what's missing. They're now going to act and react to a cage. You got to think about what that means. If you were in a cage, you'd probably act differently than if you were out in the field yourself. The field of the Bronx, for example, where I am right now. And this is what I'm trying to get to in terms of the work we're doing. We have this wonderful notional idea. We built a model, and we're going out and getting data. We're not getting any data. We're getting data that is relative to a set of questions. And those questions generate hypotheses. We further take those hypotheses and parameterize them. We try to make them measurable in the sense that they can possibly relate to something we could experience and observe. All of that takes, and then we go out and actually get observations of data and mash them together and come up with plausible hypotheses. And how plausible are they is the question. And then choose a range of hypotheses that are the most plausible. Okay, we did all of that for 3 different kinds of data: binary, integer, and continuous data. But it's still very notional. The question is not so notional. It is embedded in a set of realities, like a labor market. I'm calling it a market. It's notional. It's people trying to find work. And there's an exchange, a commerce. The original word commerce means exchange. Take goods together, and there's an exchange. There is an agreement. Einstimmung, tuning, a Übereinstimmung in the German, has a great way of putting that. An agreement between 2 parties. Overarches the 2 parties. And all of that is embedded in what we're trying to do here. Only we're just taking the analytical thread through that. We cannot forget that, as I say in the prolegomena to my book on Stats 1 probabilistic reasoning, we cannot forget that this comes out of an experience of real people making real decisions in very complex organizations, and even more complex ecosystems, in which there are lots of different players over space, over time, changing rapidly, revolutionarily, evolutionarily. And that's what we must always remember when we take expectations. And then that gets back to, what does the expectation mean? In our very simple case, we are using a weighted average. I'm also going to cut up things. Space and subspace feels a little bit like Star Trek. Let me put up the very first thing we're going to look at. This is a result of the previous lecture. If you want to know where all this comes from, it comes to the previous lecture. So what did we have? We had averages of performance scores going from 2, 2.5, 3, 3.5, 4.0. These are hypothetical, but these are actually terms that relate to data. Anything between 2 and a 2.5, not including 2.5. Anything including 2.5 to 3, not including 3. Non-overlapping intervals. We could also look at that, any data like this as well. We also had 2 environments in which performance could occur. A low volatility, that's half a grade point, and a full grade point volatility environment. You can think of your own performance in your own organization and situations in which you could have low and high. And we calculated, let me see if I can put this up fairly quickly from my notes. Yes, we all have notebooks, and here they are. So at a mu, an average, and here's the sigma, the standard deviation, or some notion of uncertainty. You don't even have to prove that this is an arithmetic average or that this is a squared deviations of values of data from that. You don't even have to prove any of that. Gauss did that for us. So did Marquis de Laplace. We have 2 independent, mutually exclusive, completely exhaustive hypotheses about the uncertainty in the environment. At a level of mu, we get 0.002 plausibility and 0.0 or 3 plausibility. If we add these together, because any mutually exclusive, completely exhaustive set is, let me put this in red. Oh, give it a nice. We want to add either or situations. It's either going to be a lower or high volatility. Add these together, and these are going to come up to, if we were to round it, 0.05. And we can take the rest of these, 18.2, 0.367, 0.014, 0.000. Okay, let me put the other 4 numbers here. 14%, 16.7%. These all act like joint probabilities. Now they're normalized joint probabilities, and that helps. The other thing to notice is that they incorporate, each one of these plausibilities incorporates information across both low and high volatility at the same time, simultaneously, across low, high performance. They're all mixed together. And remember, we got that by taking the sum of the joint probabilities that we had for each of the hypotheses and then normalizing everything so they all were part of between 0 and 1, as what these are. Okay. That's what these seem to be. You add all of these up, it's going to add up to 1. And we get this 0.73 probably. And this 0.12. And if I add these across again, 18, 2, and 14 gives us 32. You can put it on pause and do it yourself and see if you got the idea right. 3, 36, 7, 16, 7, decimal 4 gives us 53. Oh, winner, right, yeah, the highest plausibility. Next highest is a 2.5. Grade point A, 0.14073. If I got my numbers correct, 0.9, rounding up, and 0.1. If I have my numbers correct. I can also go in the other direction and get 56, 44, 99, 44, 100% pure ivory soap. Yes. And those all add up to the magic 1.0, either in this direction or this direction. So far, this is just a reiteration of everything we've already done. Now, the weighted average. What is the weighted average? If these are, there's a couple of ways of doing this, but I'm going to take this very simply. If these are the outcomes, the weighted average ends up being 5% of the time we see a 2, or 32% of the time we see a 2.5, or 53% of the time we see a 3, or 9% of the time we see a 3.5, or 1% of the time we see a 4. These are all either or. Either or. And thus we add. And we're looking at contributions of 2. 2 weighs in at the level of its plausibility. Oh gosh, if I take these mu's, this is probability of a mu. Unconditional, by the way. Very important. That's unconditional. And they add up to 1. These are probabilities down here of sigma, also independent of one another, and they add up to 1. I multiply the mu's times the probability of a mu, I get 2 times 0.05. And that should give us I think that's 09 if you take into account all of the 0.1, right? In the rounding. I made it that way for the rounding. 2.5 times 0.32 equals 0.805. Now these are grade point average. We're working with GPA units. That's 0.09 grade point average. That's not your total. That's the contribution of a low level of grade point. And this is a theoretical level that we are generating, which the data actually generates and is baked into these probabilities. So the data is in here. Remember, each one of these, the probability of mu equals 2, given a sigma equals 1, and all of the GPAs we have, that number equals 0.043. It's all baked into those green probabilities. So data is in here. So you can't say that it isn't. I just said it was theoretical, it really isn't. That's wrong. Oh, like, yes, okay, then we get 3.0 times 0.53. So this contribution is going to be the highest for 2 reasons. One, it is the most plausible, and it has the highest, a fairly high performance level. And we have 3.5 times, quickly there, 0.09, and that adds up to 0.3045. These decimals are getting nonsensical. It's as if we're forming a forecast. And this is a very crude way to do this. Typically what we would do is we would do some sort of sampling of potential grade points using the schedule of probabilities 1,000 times, come up with other statistics that would be very useful. And some of those statistics we're going to be coming up with at the end of this. There's great expectations, and they're going to be called quantiles, and those are, in a sense, expectations as well. And we're actually going to use that. We're going to the secret share bit here. We'll use that to see if we can find outliers. I don't know that we can or we can't. We'll see. Okay, 3.5, 4.0. And this works out to 0.48. Okay, so there's our weighted average. We then just simply add each one of these up. Each one of these is a contribution. Let's get out the layer. And all of this adds up to 2.8495. Okay, so that is the weighted average. That is the weighted average right there. Now let's do something really crazy here. Let's think about what would be the average grade given this entire setup, all of the data we used, all the hypotheses, that the data is somehow concentrated at a mean, the hypothesized mean, with a variation. Remember what we had. Hypothesize this. We had some sort of curve, courtesy of Dr. Professor Carl Friedrich Gauss, where the hypothesized mean is in the middle of a symmetric curve, and where deviations from the curve start to change direction from increasing quickly from one end, hitting an inflection point, to decreasing, and then going to the next one on to the other end. And that somehow between here and here, which is one standard deviation, that's how the standardization of sigma comes about. It's very standard, plus or minus 1 on either side at a key point of that curve. Okay, a lot of assumptions involved, but turns out they're quite reasonable, and you can see them in nature, and we actually use the Galton board, Francis Galton, 1870s, 77, to show that we get the same result all the time, and it's really a binomial result. It's really a Poisson result, which is really this continuous result. And oh, and by the way, just to remember this, roughly 67% of all of the plausibility is between these two goalposts. Just one or the other, and that's a great rule of thumb that we often use. Just remember, we have all of that baked into this. Now we ask the question, what is the expectation of grade point average for, in our system here, any GPA greater than 2.5? Well, that could get a little confusing, but let's say GPA, yeah, I don't even want to try that, greater than 3.0. Okay, now it turns out that these are intervals. Go from 2, 2.5 to 3.0, 3.5, 4.0. They're non-overlapping intervals. I start here and end almost there. I start at 2.5, I end almost at 3.0. I start at, and these open circles mean up to but not including, here, and go up to here. The last one, however, boundary condition, whatever the heck that means, non-overlapping, and everything's being accounted for. Okay, what if I wanted to see anything greater than 3.0? Well, you can address it this way, but logically it's probably greater than or equal to 2.5, in which case I need to carve out this part of the analysis. Okay, that's how I'm going to do it. And we'll let wording be whatever it is. Okay, which means it isn't these, it's not those, it's just 3.5, 4.0. Come up with wording for yourself that says, what is the probability of getting a 3.0, that point, anywhere between there and 4.0, inclusive, I guess. We got to be logical and we can be legal, and I will find my lawyer and we will write that up. But what I want is, I want to include 3, 3.5, and 4 in the analysis. I have plausibilities of 53, 9, and 1%. And what I was saying about this is subspace. The space of everything is 2 to 4 inclusive, and this subspace is 3 to 4 inclusive. Subspace, it is a partition of the full set of an analytical ideas about notions about mu. And yeah, this whole thing is a notional analysis. I'll also grant that notion. And we can get notional set, not real assent yet, as in John Henry. Okay, okay, fine. We'll leave all of that aside just for the second. Well, maybe for several seconds till another time. So I'm going to carve this up. Now, what is the correct way of doing this? If this is now my new space, and I have an outcome of 3, 3.5, and 4.0 with relative, and this is where the idea of relative plausibility comes in, 9, 1. I have to add these up into, what is 3 and 9 and 1? Is that 13? All of these add up to 63% of plausibility. So if I have a mu centered at 3 and so on, from here on out, I get 63%. Okay. This tells me that the average, the weighted average is 28495. So if this is equal to 2.8495 here in the middle, okay, somehow I got 63% above this. Okay, this is lopsided, beautifully lopsided. This is lopsided. Notice between 2 and 4, I actually have some weight down here. Oh, very anomalous. Yeah, okay. Purists are going to go nuts here. Isn't he talking about a Gaussian curve? It always has to be. Yes, it does. But I probably needed to stretch this down to 0 so that you can get a better idea. Okay. Pedagogical issue, not a realistic issue. Something I wouldn't worry about at this point. Let me pull these folks away. Okay, good. That's convenient. I want to take the 53 and divide it by now. $63. The 9 by 63. The 01 by 63. To normalize them. Because if this is my entire new space with these plausibility numbers, I need to now normalize these in order to have probabilities, or else my number will be way off. Way off because it will be biased away from 63%. It's only 63%. Yeah, but in its own little world, its own little hobbit world, if you will. In the grand scheme of things across Middle Earth, it's 63, but in its hobbit world, it is 63 divided by 63, 9 divided by 63, 1 divided by 63. And these probabilities end up being 84. Let's see, what did I have? 84, 14, and 2. Relatively the same idea. If the ordering is correct, 3 is bigger than more plausible than 3.5 is more plausible than 4. And okay, transitivity and everything else happens. Ordering still works. I think these had better add up to, and they do, 1.00. So we normalized our condition here, looking only at this subspace, labeled hobbit world. Okay. Bilbo Baggins and his 11th. I think it's 111. Everybody's birthday preparations. There we go. And here we go. And I multiply these times 3, 3.5, and 4. When I do that weighted average, 84% of the time I get 3. That comes in at 253. I'm sure you can do this faster than I can write it. 3.5 times 14% is 48. Much lower contribution, of course, and the least contribution of all. And even though it's a high number, 4 only comes in at 2%. And given this portfolio of plausibilities, you can tell I'm from finance. And you add these up together, and we get a grand total of 3.08. Not surprising. It's close on 3. But there's not much hope for it being a 3.1, a 3.2, not a 3.5, not a 3. Okay. The expectation would be right around 3. If we believe all of our analysis and all of the assumptions of our analysis, and cutting up the data into these hypothetical ways, you believe all of that, and if you believe this that I'm pointing to, that the way we looked at data in the first place was normal. We don't want to use the normal. I don't use it. I say for now on, we're not going to talk about the normal curve. Just like when you are giving directions to somebody in a car, and you say, go right. And the driver then says, do I go right? Right? Meaning correct. Okay. It's very confusing. Yes, it's correct. Then we'll use the Spanish word directo. Okay. Or gauche and droit. All right. Something different. So the right way, droit means the right way, right? The right as in law. Okay. And same with normalize and standardize, and standardization that we saw with is the Z value, where we take any of the GPAs, get their deviations, and scale them by the standard deviation, the thing we call the standard deviation. And we see here over here why it's called the standard deviation. Okay. Somebody's notion of standard, it's not the normal distribution. Okay. You got to Carl Pearson immediately in the, I think 1899 or 1901 or whatever, when he did this, immediately say, oh my God, I should not have ever called this normal. That's some interesting mathematical normal properties. Perpendicularity, okay, that whatever that is. Okay, so we have 3.08 here for the subspace. Now, I've gotten two of the three things I wanted to do done. The third thing is, okay, I want to get a notion of an outlier. And I have 5 ways to do that. I'm going to show one way, outliers. Suppose we have this data. So, magic of TV here. Special effects, we have outliers and we have a set of data. Now, the first line is the data as it occurs across 8 performance periods. If you're a student and these look like GPAs to you, and you are in an undergraduate program and you have 4 years, 2 semesters per year, there we go. There's your performance. Actually, looking at this, I'd be pretty happy. Probably semesters 6, 7, and 8 are semesters in which you're taking your the courses you really like. I hope, probably your major courses. And the last semester you're looking for a job, so we fall down there, or you're taking some really hard courses. The other ones you've had quite a little interesting time, especially the 3rd semester, and then the 4th and the 5th. And I see improvement here. I would actually be looking for that in that process. We do have people among us who are nearly 4.0 all the way through, and a gazillion extracurricular activities. Oh my God. I guess I would have challenged them even more. But I mean, given the curriculum, here we are. We want to ask the question, are there any outliers? Now, there is somebody by the name of John Tukey around the late 70s, around 77, came up with something called, that's not the Economic Development Agency, that is exploratory data analysis. Let the data tell us something about itself. And it's exploratory. Now, what's he after here? He's after the following, a famous plot called the box plot. See if it's from George Box or not. Do that. There's the box. What we want to do is we want to get the 50th percentile. In other words, find out, given the sequence of 8 performance periods. Don't look at the blue thing yet. 50% of the observations are above and 50% of the observations are below what number? And then we also want to figure out the 25th percentile, which we'll call the first quartile. In the third quartile, 75% of all of the observations are below what number? We also have a min and a max. This is a typical summary of data. Notice we're not calculating standard deviation, we're not calculating means, we're not calculating anything else. We're just going to sort that data into an order from lowest to highest. We could also do highest to lowest. Lowest to highest, we're going to do order statistics. And the most primitive of this kind of oops. I can hear academics, professors, other people go, they're not the most primitive. They're actually some more primitive. Yes, there are. But the ones that we use practically, the base ones, are percentiles. Just like the 25, 50, and 75. And these are typically called quartiles. Q1, Q2, Q3. 100% is Q4. That's the max. Okay, glad I caught that. Technically, that's Q4. And maybe you could call that Q0. Okay, fine, just to be complete. Nobody uses that that I have seen. I'm sure there's somebody out there who has in some laboratory. These are called order statistics because we're looking at the order. So first job is we sort this into a different index of 8. The order in which not they come, but that they go from lowest to highest. We have two different orders here. The green natural order of things, okay, going through multiple years and semesters in each year, or the mathematical order of things from lowest to highest. And that's the thing that we're going to focus on to do these order statistics. So the first question is, go back to using red. We have 8 items. What is half of 8? It's 4. 2.2 is no. Look at this. Look at this. We have 8 items. Where do you think the middle is? Oh, well, let's bring this back up. That was interesting. I literally breathed on it. Okay, where is the middle? The middle is probably, and this is again, use some common sense here. Right here. We have 4 above this line and 4 below. That's what we're going to call a measure of, we're going to get a measure of central location. And it's smack in the middle of 2.2 and 2.9. You could take the average of those two, and come up with a number that we could call the 50th percentile. Another way to do it is to take the distance between 2.2 and 2.9, which is 0.7, and add that distance to the lowest number. And that too is correct. And we often use that as a linear interpolation device. But yeah, you're right. It's the same. Yep. Okay. Well, actually, it isn't. I need 1/2 of this, don't I? There we go. Can't remember his own formulas? No, because I'm always thinking through them in process. I want to get halfway between 0.7, which is the distance between from here to here, and that'll be 0.35 on one side, 0.35 on the other side. So, okay, 2.2 plus 3.5 is 2.55. There's my answer, and I'm sticking with it. We're going to call this the median. The 50th, I tend to use, instead of quantiles, I like to use the more generic term, instead of quartiles, quantiles. Change the N out there, okay, and for R, and you get quartiles. Quantile is nothing more than a percentile. In fact, that's what it's going to be called in Excel. Everywhere else in the universe of math, and so it's called a quantile. I'm sure there's exceptions to that. Okay, so 50% are above, 8 are above, and 50% of the observations are below 2.55. Everybody could agree to that, I think, pretty easily. We'll call that the median. And it's kind of an average in a sense. It's an average location, where average is now expanded into the arithmetic average of these integers, which is 4.5, a non-integer. Okay, confusing, I agree. So what about the 25 and the 75? We do much the same thing. We ask the question, 25% below. Well, that's easy for this. It seems to be easy for this because this is actually the hard case where we have to say, well, we have 8, and what are we doing? We're dividing it up into 4 equal segments. Let's put the 75 in here. So we have 8 here, and we have 1, 2, 3, 4, 5, 6, 7, 8. So that's the notion of quartiles. Those Q1, 2, and 3 on the bottom. So here's the 25th. How many are there? Okay, so it's the same issue. We have to bridge the gap between the second and the third observation in order, not as they come in nature, out in the wild, called an undergraduate program and your participation in it. No, between these two in order. So it's between 2 and 0.1 or 0.05, 2.05. Half of that. Yeah. So we got 0.1 over here, 0.1, 0.05. Just doing this in my head. Check it. We're going to say this is 2.05. And the other bound up here, the 75th percentile, says 75% of all of the observations are below this number. You can see. Oops, should have used that. Okay. There we go. And it's half of that 2 point. So you can, pretty sure that's going to be 3.35. So we have 0.6. Here, f of 6 minus 1. That's equal to what? F of 0.5. What's that? 2.5. Add that to 0.10. You see, I just 3.35. Okay. So we have our three numbers. And you go like, oh, wow, now what are we going to do? What's got the out? Is the outlier anything greater than 75 or less than 25? In which case we have 2 and 2. We have 2 outliers on either side. We have 4 outliers. Yeah, that could be our number. But Tukey says, and there's another person that's going to do this, Chebyshev, later on, was going to be really conservative. It's not an outlier unless it's way the heck out, on the fringes of the expanding universe out. Okay, that far out. What Tukey says is there's a lower bound that's equal to Q1 minus 1.5 times something he calls, well, it's been called this for a while, the IQR. What is the IQR? It's the interquartile range. Now, if we didn't use quartiles and we use something else, quantiles or whatever, use the interquartile range. But look at what it is. IQR is the difference between Q3 and Q1, between the 75th quantile and the 25th quantile. Now I could have divided these up into 4 uneven pieces. And so why was this? It was easy to do. It was easy in the days before we had machines to do it for us. It was easy for an analog machine to build it. Okay, there we go, done. We could have used an upper lower bound of 5% and 95%, or 2.5 and 97.5%, just as easily. But 50 is almost always 50. That's easy. Okay, that's a real good, robust measure of central location. So What is this equal to? Hopefully you've calculated it all by now. 3.5 minus 2.05 equals 1.30. I got my maths right. So it's 1.30 standard deviations in that sense. The standardization here, but not under a normal curve. It's under whatever this thing looks like, whatever this data looks like. Very empirically oriented approach. Okay. All right, fine. Put it in here. 2.05 minus 1.5 times 1.3. So what's 1.5 times 1.3? 1.95, it turns out. So 2.505. And that is equal to 0. If my math is correct, if it isn't, you can correct it, but I'm going to get pretty much the same thing. 0.4. .1. Grade-point average of 0.1. It's way down here. And the Tukey fence goes down here. It's below the minimum. Therefore, there is no outlier down there. Okay, if we went down, we can go back up. Let's try that. And there's an upper bound equal to, instead of Q1, Q3, instead of minus, plus 1.5 IQR. And why 1.5? Oh, you can try to find that one out. There's some lore around that. It has something to do with lots of experiments and kind of like a bootstrapping of what's the right limit. Okay, how many of those IQRs do you have to go beyond in order to get something truly in the tail of a distribution? That's the idea. Okay, principled, not quite. So what was Q3? 335 plus 1.95. Don't have to recalculate that every time. And this gets us what big number? 5.3. Well, it's greater than 4. That's the important thing. That's way above the max. So I think we can say we have no outliers. Right? Pretty good. Okay. 0 outliers in this data. Well, I mean, if you had a grade point, even if you had a 4.0, it wouldn't probably. It wouldn't in this 8th semester thing. Remember, it's order statistics. Suppose that 1.75 was a 0.1. That would have worked. Yeah. It doesn't matter what the level was, what the level of these grade point averages were. It's where they are in their rank order. Let's call it rank order statistic. Very different way of looking at things than we have looked at things at all up to this point, but all based again on distributions. This is just the ogive. And if it's just the ogive, we should be able to plot an ogive between 1 okay, I guess 0. A minimum of 175, right about here. And that has Okay, we'll just put that there. And a maximum of 375 about here. Okay, when we get up to that point, we have 100%. Here we have 0%, starting at 0, and we have 100% at this point. So let's see, I can put that up. And then we're going to have some relationship between these two. Okay. 2.05 is 25%. So let's mark this off at 50, 75, 25. What am I marking? I'm marking off the cumulative relative frequencies in the order statistics cell. So I've got that. Let me use green here. We're starting off here. We're ending here. So my physics teacher told me to do years ago in high school for observations. Okay, put a dot and a circle around it. Okay, follow directions the rest of my life. 2.05. That's right about here. Uh, 2.55 for the 50. Right. Okay, there's a little bend going on here, and I'm happy to see that. 3.35 is the last one. And that's about here. Let's connect dots. There we go. The so-called ogive. I suspect, though, you can use this to interpolate in between any one of these elements. In order to get any intermediate value, continuity of numbers. You see, it's what we call monotonically increasing. Oh, kind of, sort of, yeah, okay. Kind of going up like this and over like that, a little ogivish. All right, the ogive. We'll do a little bit more work with the ogive when we attempt to put all of this stuff into a spreadsheet in part 2. Okay, for now, what have we talked about? We talked about Jane Goodall a little bit. What did we talk about? Go to the field, get your information, and pose your questions. That's what I get out of Jane Goodall, among other things. Go to the field. Don't capture your data and put it on the side and think that you're going to be able to observe, especially human being generated data, in a petri dish. Won't work. Won't be the same thing. Never is. People act and react to different things. We found this with enterprise risk management and analytics in large complex organizations. We take people off to the side. They talk differently than when they talk inside with their boss. Okay, you need to recognize that brought up that way. Okay. The second thing we did was we did expectations. We built a very simple calculation machine, not only for the entire space of potential levels of performance, with plausibilities that have into it actual data. That's the key there. Actual data is inside of those plausibility numbers, and thus inside of this weighted average. It isn't just dreamt up. We actually observe something and put it into it, into our notional analysis. So it gets a little bit more real and more objective that way. But then we took a subset of that, a subset, called a subspace, where we had to renormalize in order to get the correct number at about 3.8. That's where that one was. Okay. It could be greater than 3, and it will be greater than 3. Okay. So quite a bit there. And then finally, we looked at this is really truly an heuristic way. There are a couple of principles here. One is we use an order statistic called quantiles or quartiles, divided everything up evenly into 4 nice even pieces, in this case with 8 data. And this is the hard case. If we had 9 data points, it'd be actually a little bit easier to do. You'd have a number that we wouldn't have to calculate anything. But I always choose the even number because that forces us to think a little bit about what we mean by a number in between 2 other levels or ranks of data: second rank versus third rank versus fourth and fifth versus sixth and seventh. We made a box plot and then invoked Tukey, John Tukey, to give us an idea of how to create 2 fences, both of which are so far beyond the pale that, according to John Tukey and this set of analyses, we do not have any outliers in this data. And finally, we plotted an ogive. God help us. Next stop will be part 2 on a spreadsheet where we can play with the numbers even more, even these outliers, and use some of that computational platform's percentile capabilities, and we'll see if our percentiles come up with theirs. All right, that was fun for me. Hope it was interesting for you at least. And you could always fast forward when you don't want to listen to me anymore. So anyways, I do thank you for your kind attention. And I'll hand this over to the ghost in the machine that does the compilation. And then I will send it into the cloud onto YouTube for you to, as you're going to go and see it anyways. Okay, take care and be kind. Thanks.